Well, hey everyone, and welcome back. As you can see, we've got another topographic profile drawn out here as a sort of a continuation to the last video I made, which detailed how to calculate slope from a topographic map. Now, that mostly just required basic knowledge of algebra. However, here we're going to tie it back into a concept from geology, that being dip. Now, of course, I think I discussed at some point previously that you can calculate the angle of dip, or get a general good idea for the direction of dip, excuse me, just by looking at the compass direction on a topographic profile, right? We've got northeast, southwest. So for any given strata, it could be pretty easy to tell in general where they're dipping. However, when it comes to calculating the exact angle of dip, using some of the concepts we use when calculating the slope of a particular region on a topographic profile can be incredibly useful. So as you can see here, just by getting a brief look at this, we've got what appears to be the side of a hill or a mountain where we've got a rapidly decreasing elevation. This is sort of one of my favorite things to draw, just basic hill-shaped thing. We've got a rapid decrease in elevation right here, then it sort of just gradually levels off. And of course we've got our units. This one is apparently 200 meters above sea level. This one right here is 100, so then we see it levels off around 80 or 60 meters above sea level. Okay, and we've also got the scale up here just to give us a relative idea horizontally what we're dealing with. So 1 inch represents 20 meters. Okay, so for this problem, or this example, I want to calculate the dip within this region, right? Now, you'll notice I've drawn these dotted lines that I sort of drew just to represent a strata that is poking through at the surface in this area, in the area boxed off by those dashed lines. So that's going to be particularly important, just in identifying which, for the sake of being practical, we're identifying a given strata that we're talking about instead of just looking at the land on its own. Although it could work that way too, but anyways. So if we want to look at this piece right here, let's say we want to calculate the dip of the strata in this region, particularly right around where we see these lines that are quite condensed and therefore have a much greater slope or are much steeper than anywhere else on the profile. So if we want to find the dip in this area, then it's very simple. We have to start off by just finding the horizontal displacement and the vertical displacement across this area. So let's use the dashed lines as boundaries, and we'll just go roughly in the center of this sort of curve here we have. So it's about 4 inches roughly, rounding. It's about 4 inches wide at its center. So we just do 4 times 20, that's our scale factor. So we move about 80 meters horizontally. And then to calculate our vertical change, we just look at, okay, this one, if this is the 100 contour line, then it appears as if we're going by 20. So we go 200, 180, 160, 140, 120, 100, right? So this line appears to be somewhere between 100 and 80, much closer to 100. So we'll say, just rounding again, it doesn't have to be perfect when we're dealing with things between contour lines. We'll say that delta V is going to be something minus 90, actually. We'll go from our upper value first. This one appears to be more in the middle between 200 and 180. So we'll call that 190 minus 95, which, hey, what do you know? It's 95 meters. Okay, so we know our horizontal and our vertical displacements. However, we aren't just going to plug that into the slope formula, m is equal to y over x. We're actually going to use these in calculating the dip across this region. So to help visualize this, let's just draw a little line across here, right? that's roughly where I calculated my horizontal and vertical displacements from. So it's going to be a relatively good representation. Now when you think of what this line is doing, it's actually showing us the sloped surface, okay? So if we want to think of this in 2 dimensions, although 2 different dimensions, not from a top-down perspective like this, but from a side view, then this is going to be what is essentially the parabola on a right triangle. In fact, let's give these guys points. We'll call this x and this y, a little line segment there. So x appears to be our lower one. We'd say this is right here. Y appears to be our higher one. We'll call this y. And so we can set up a right triangle using our delta h and delta v when we think of, okay, the horizontal change is going to be the distance we move, forward or backwards or to the side. That's going to be our distance across, horizontally on the triangle. And our delta v is going to be the vertical. So we can just sort of finish this triangle here. Make it look something like that. It is a right triangle. And now we just plug our values in. This is not drawn to scale. And if you recall, the dip is the angle that the strata makes with the surface, okay? So when we think of this, this is x. X is at the surface, right? And then it continues to move upwards. So we can think of it like this. The surface moves backwards. It goes in back of x. Behind x, actually, it appears to be dipping at a slightly different slope. It's not perfectly flat. But this will actually make this a dashed line to represent the flat horizon, right? And behind x, maybe it starts to slow down a bit and dip slightly differently. And then we know that below x, well, we've just got something else going on. If we were to think of this as a 2-dimensional cross-sectional diagram, we've just got, maybe we've got this strata continuing to dip at the same angle, but other stuff going on. This is all below the surface. Okay, so when we think of dip, well, what is dip? It's the angle that is made with the surface. So that actually is this little angle right here. We'll call that phi, or phi, or however you pronounce it. I don't know. Some people say, oh, well, since pi is pronounced pi and not p, it's got to be phi and not phi because the letters are I don't know. I don't care. I think phi sounds better, so that's what I call it, but to each their own. So if we want to calculate this angle, well, we just go back to simple trigonometry. The tangent of this angle is going to be equal to the opposite side divided by the adjacent side. SOHCAHTOA, yeah? So if we want to find angle phi slash phi, then we just say that that is equal to 95 divided by 80, and then we can do the inverse tangent or the arctangent of each side. Theta is equal to the arctangent of 95 divided by 80. I do not have a calculator ready on me, unfortunately. I should have prepared for that. But hopefully it's simple enough from here. You would just plug that into a calculator and then it would spit out your answer either in radians or degrees. And that would be your angle of dip because it is in fact the angle that it makes with the horizontal, the surface. And then of course if you wanted the direction of dip, you would just look at this. Well, let's see, this line, if we were to just draw that going through the compass bearing, that'd probably be, if it's dipping down like that, that'd probably be north with a slight offset to the east, right? Somewhere in the northeast realm. And with that you can find both components of dip from your topographic profile. And of course then we know strike is just perpendicular to dip, so you can even find strike. What do you know? But that's about it for this video. Hopefully it was informative, otherwise good review. Hope you guys enjoyed, and I will see you all in the next video. Ciao.